Continuing on from page 3 of the Polynomials booklet, find the square roots of 5 minus 12i. Now we did do this in complex numbers, so this is a review. Remember we let z squared equal 5 minus 12i, where z equals x plus yi. So therefore, x plus yi, or squared, is equal to 5 minus 12i. Expanding the left-hand side, we've got x squared plus 2xyi plus y squared I squared equals 5 minus 12i. Simplifying that, we get x squared. Now, I squared is negative 1, so we've got x squared minus y squared plus 2xyi is equal to 5 minus 12i. Now we can equate real and imaginary parts. So equating real and imaginary parts, we get that x squared minus y squared equals 5 as my first equation, and my second equation would be that 2xy equals negative 12. Rearranging that second equation, I've got that y equals negative 12 over 2x, which is negative 6 on x. Now I can substitute y equals negative 6 on x into equation 1 here. So I've got x squared minus negative 6 on x all squared equals 5. And just going to multiply, so let's just do that. So x squared minus 36 on x squared equals 5. Multiplying through by x squared, multiplying each term by x squared, or left-hand side and right-hand side by x squared, I've got x to the power of 4 minus 36 equals 5x squared. Bringing everything over to the left-hand side, I've got x to the power of 4 minus 5x squared is 36. Factorising this, I've got x squared minus 9, x squared plus 4 equals 0. And further factorisation gives me x minus 3 times x plus 3. Now remember that and x squared plus 4 is 0. Sorry, I'm off screen. So therefore, x equals 3 or negative 3. Now, remember that z is x plus yi, but the x and the y have to be real numbers, so you do not go here. You don't come over here and go x squared minus 4i squared to make it a difference of two squares, so x has to be real and y has to be real. There's your imaginary bit there. So we solve only x is 3, and I'm going to put here, and x is negative 3. So when x is 3, let's just substitute over here. When x is 3, y is negative 6 on 3, which is negative 2. And when x is negative 3, y is negative 6 on negative 3, which is positive 2. So therefore the square roots, so just conclusion, therefore the square roots are, now when x is 3, y is negative 2. I remember my roots are x plus yi, so it's 3 minus 2i. And when x is negative 3, y is positive 2, I've got negative 3 plus 2i. And they're my square roots. Okay, now we're looking at questions of the type. So we're looking at the equation z to the power of n equals a constant, or equals a. Sometimes a is a constant, sometimes it's not. So the solutions of the equation z to the power of n equals a, where a is a real number, sorry, it is a is a real number, and n is a positive integer, are what we call the nth roots of a. See, because if z to the power of n is a, so for example, if n was 2, then the square root, then z would be the square root of a. If n was 3, then, so for example, if z squared is a, then z is the square root of a. If z cubed is a, then z is the cube root of a, etc. So therefore, if z to the power of n is a, therefore z is the nth root of a. That's what that is saying here, okay? So first question is to find all the solutions of the equation z cubed is 1. Now, last year in complex numbers, we used the method where we used the Moyer's theorem, and we represented z cubed as r cubed plus 3 theta and 1 as 1 cis 0, and then we equated the moduli and the arguments. We're not going to do that this time. So I've got z cubed equals 1. So therefore z cubed minus 1 equals 0. So we're going to solve this as a polynomial equation. Now this really is a difference of 2 cubes because z cubed minus 1 cubed is 0. So we're going to solve this through factorising. So let's factorise z minus 1. Remember the factorisation for a cubed minus b cubed is on your formula sheet for 2 unit. It's in factorisations. So it's z minus 1, z squared plus z. So it's z squared plus z times 1 is z plus 1. That's that factorisation. Now, we obviously can see that z is 1, or z squared plus z plus 1 is 0. Now we know that we can't factorise this. So we're going to use the quadratic, because two numbers that multiply to give 1, 1 and 1, don't add up to 1. So we have to use the quadratic formula to work out z here. So we've got z is negative b, which is negative 1 plus or minus, square root of b squared, which is 1 squared minus 4 times 1 times 1, over 2 times 1, which is negative 1 plus or minus. The square root of 1 minus 4 is the square root of negative 3 over 2. Now writing negative 3 as 3i squared, I can now, I'll just keep going over here, so therefore z is negative 1 plus root 3i over 2, or plus or minus, I can just put that. So square root of 3i squared is root 3i. So it looks like my other solutions, so all my solutions are z equals 1, negative 1 plus root 3i over 2, negative 1 minus root 3i over 2. Okay, so they're my 3 solutions. Now, let's just relate that back to how we used to do this before. Remember that, for example, 1 cubed is 1. So one of my solutions is here. Remember, if you've got 3 roots, they'll be equally spaced around the circle. So the roots are actually there, here, and there. And this angle in here, if you were to use the methods that we learnt last year, that would be 2 pi and 3, that would be 2 pi and 3. The angle between here is also 2 pi and 3. Okay, and the moduli are 1. Okay, and that's 2 pi and 3. And they're all 1 unit from the origin. Okay, and the solutions, the way we would have written them last year, would be 1 cis 0, 1 cis 2 pi and 3, and 1 cis negative 2 pi and 3. And if you actually evaluate cis 2 pi and 3, you will get, well, that's cos 2 pi and 3 plus I sine 2 pi and 3. You would get this one here. And cis negative 2 pi and 3, you would get that answer there. Now for the last question on page 3, find the 4th roots of 1. So if z to the power of 4 equals 1, then z to the power of 4 minus 1 equals 0. So that's really z2 squared minus 1 squared is 0, and we can represent it as a difference of 2 squares. So that's a squared minus b squared is a minus b, which is z squared minus 1. A plus b would be z squared plus 1 is 0. Now we can factorise z squared minus 1 to be z minus 1 z plus 1. And we can write z squared plus 1 as z squared minus I squared, because I squared is negative 1. And so therefore, continuing this factorisation, we've got z minus 1, z plus 1, z minus I, z plus I equals 0. So therefore, z is 1 and negative 1, so it's plus or minus 1, and it's I and negative I, which is plus or minus I. Now, if we actually draw these, if I do the same thing as those and show these where they are, my 4 solutions are 1, negative 1, I, negative I. Notice that they are separated by an angle of 90 degrees between each of them, and they all have modulus 1. Okay? So they would be 1 cis 0, 1 cis pi on 2, if I was to write them in modulus argument form, 1 cis pi, that would be here, pi, and 1 cis negative pi on 2. Okay, would be the negative I there. Now, another way that we can factorise polynomials is by completing the square. Now, there's a few ways we can complete the square. One way is to change the last term, and we would change the last term if we have a z squared and a z term, and we'd change the constant so that it will complete the square for us. So this is very much a 2-unit concept here. So z squared plus 4z plus 8. Well, that's really equal to z squared plus 4z. Now, to complete the square, we halve the 4, which is 2, and then we square it, so we get plus 4. But I'm going to write down what I've got. So I've got z squared plus 4z plus 4. We're adding that, then we take it away, then we put plus 8 because that's what we originally had. So these three terms here complete the square. So I've got z, they make z plus 2, all squared, and negative 4 plus 8 is plus 4. So now I can factorise this. At the moment it's a sum of two squares, but I can write it as a difference of two squares by writing plus 4 as minus 4i squared. Now I can factorise this as a difference of two squares, and I've got z plus 2 minus 2i times z plus 2 plus 2i. And so therefore, yes, that's it. I've factorised that over the complex field. That's done, okay? But you could also write it as z, oh no, that's fine, all good. Now, next question. If you have to complete the square and it's a non-monic quadratic, you will take out the coefficient of the leading term, and then you'll have to deal with some fractions later. So we've got 2z squared plus 4z plus 3. Well, that is equal to 2 bracket z squared plus 2z plus 3 over 2, because this is not an even number, so this 2 balances out with that, and you've got 3 over 2. So now let's keep this 2 out the front, but we just basically complete the square here. So we've got 2 bracket z squared plus 2z. Now, if we halve the coefficient, remember to get the last term, we halve the coefficient of the z term. Now, 2 divided by 2 is 1. 1 squared is 1. So I'm adding 1. Then I subtract 1, and then I'll just keep my 3 on 2 there. So I complete the square using these three terms here, and I've got 2 bracket z plus 1 squared, but I need double brackets here, because then I've got minus 1 plus 1.5 is plus a half. Now, this is a sum of, I can write half as a square number, I can write it as 1 on root 2, but I need a difference of two squares, so I've got 2 bracket z plus 1 squared minus, now if I times this multiplied by, if I write it as negative I squared, over 2, it's now a difference of two squares, because I squared is negative 1, negative 1 is positive 1. So now I can factorise this. So I've got 2 z plus 1 squared minus, I can write this as I over root 2 squared, so now it's written as a difference of two squares, which is z, now it's in the form of a squared minus b squared, so it'll be 2 bracket z plus 1 minus I over root 2 bracket z plus 1 plus I over root 2 close bracket. Okay. The last question on this page is to complete the square with the middle term. So normally we complete the square with expressions like x squared plus 4x plus, and we have to work out what the last term is. But you can also, we can also complete the square with expressions such as x to the power of 4 plus 4, where we're missing where the missing term, for example, is an x squared term, and in this case it would be 4x squared. So remember, we can complete the square on things like this. So let's start with x to the power of 4 plus 4. Now that is equal to x to the power of 4. See, this is really x squared. So actually what I'll do before I do that, that's really x squared plus 2 squared. So if this was a squared plus b squared, you're really missing the 2ab term in the middle, which would be plus 2 times 2 times x squared, which is 4x squared plus 2x plus 2 squared. So what I've done, if this is your a squared plus b squared, I need my plus 2ab, so it would be plus 2 times x squared. That's my middle term. I can't just add that in there. I've got to take it away as well. So therefore, this is a completed square, which is x squared plus 2 all squared. And here I've got minus 4x squared, which if I write it as a difference of 2 squares, I've got x squared plus 2 squared minus 2x all squared. Now I can factorize that because that's of the format a squared minus b squared. So it'll be x squared plus 2 minus 2x, x squared plus 2 plus 2x. Now if I rearrange those, I've really got x squared minus 2x plus 2, x squared plus 2x plus 2. Now I can complete the squares on these as well. So to complete the square on the first two terms, I halve the 2, which is 1, so I add 1. So I've got x squared minus 2x plus 1 minus 1 plus 2. And here as well, x squared plus 2x. Plus 1 minus 1 plus 2. Sorry. Okay, so here I get, that's completing the square on these, I've got x minus 1 squared, minus 1 plus 2 is plus 1, and here I've got x plus 1 squared, minus 1 plus 2 again is plus 1. So now I can change these both to difference of 2 squares by changing my 1 to minus I squared. So now I've got x minus 1 squared minus I squared. Sorry, the video sort of got stuck. So I've got x minus 1 squared minus, instead of plus 1, I'm going to write minus I squared. And here, x plus 1 squared, change this plus 1 to minus I squared. Now I've got a difference of 2 squares. And I can now, that's in the format of a squared minus b squared. So I've got x minus 1 plus I, x minus 1 minus I, x plus 1 minus I or plus I, doesn't matter which one's first, and x plus 1 plus I. So as long as one's minus, one's plus. And therefore that's now been factorized over the complex field. Notice all our final terms are factorizations with x. Now if you did try and factorize it like this, x squared plus 4 is x squared squared minus 4i squared, which is x squared squared minus 2i all squared. You'd end up with x squared minus 2i, x squared plus 2i, but now you can't factorize this. You'd be stuck here and you can't factorize any further. So that's why this method won't work. That's why we complete the square by adding in the middle term. Okay.